Hello, welcome again. We were solving GATE 2014 Mechanical Engineering paper 2. Okay, we were at question number 34. Okay, so question number 34 is what is the natural frequency of the spring mass system shown below? The contact between the block and the inclined plane is frictionless. The mass of the block is denoted by m and the spring constant are denoted by k1 and k2 as shown below. So option A root k1 plus k2 divided by 2m, b root k1 plus k2 divided by 4m, c root k1 minus k2 by m, d root k1 plus k2 divided by m. Okay. So here the this theta does not have any effect on the natural frequency. Okay. As natural frequency doesn't depend upon the gravitational force, so theta is introducing only the gravitational force. Okay. So it doesn't have any effect on natural frequency. So the natural frequency can also be found by placing this spring system as horizontal one. Okay, and then a mass is placed between two springs, then the spring behave like parallel springs. So the equivalent stiffness is the K1 plus K2. Okay, so this is your equivalent stiffness and natural frequency will be your root K1 by K1 plus K2 divided by n. Okay, next. A disc clutch with a single friction surface has coefficient of friction equal to 0.3. The maximum pressure which can be imposed on friction material is 1.5 MPa. The outer diameter of the clutch plate is 200 mm and its internal diameter is 100 mm. Assuming uniform wear theory for the clutch plate, the maximum torque that can be transmitted is okay. So the given data are coefficient friction 0.3, maximum pressure 1.5 MPa, outer diameter 200 mm or 100 mm radius, and inner diameter 100 mm, inner radius is 50 mm. Okay, so these are the data given. Okay, and the torque transmitted is in clutch is given by mu w r equal. That is uniform pressure theory or it is uniform wear theory. Okay. Now the theory we have to find out the torque according to the uniform wear theory, and in uniform wear theory the W weight is given as 2 pi E max Ri bracket R naught minus Ri. Okay, then P max is your 1.5 MP, Ri is your 50 and R naught is your 100. Okay, so this is just 23561 Newton. So load is your 23561 Newton. Okay. And R equivalent in uniform wear theory is R naught plus Ri by 2. Okay. So it is 0.075. Putting the values, mu is 0.3. Putting the values, we can get torque that is 530.1225 Newton meter. Okay. Next, a truck accelerates up a 10-degree incline with a greater of 100 kg. The value of static coefficient of friction between the crater and the truck surface is zero point 0.3. The maximum value of acceleration in meter per second square of the truck such that the crater does not slide down is. Uh, now, suppose this is your um, truck and this is your crater. Okay. Now, weight of the crater is acting downward. Okay, like this, and it has the component cosecant and the component. Okay. Now, the truck is moving with an acceleration of a. Okay. So the acceleration of the truck is a. Then the acceleration, if the crater does not slide, then the acceleration of the crater will also be a. Okay. And acceleration then and suppose F dash is your coefficient of force of friction uh, that is preventing its sliding motion. Okay, sliding motion over the truck. Okay, between the there is acting between the truck and crater. Okay, So now this mg cos theta is here. The component of mg component of mg perpendicular to the plane, perpendicular to truck is mg cos theta, and along the truck is adjacent. Okay. Now truck is moving with an acceleration of a, so ma will also be in this direction. Okay. As the pressure is also moving. Okay. So to avoid relative velocity between them, f dash force is acting uh, opposite to this motion, so that it creates a development. And so, or we can say that f dash is the force of friction between crater uh, and truck, so that there is no relative velocity between truck and crater. Okay. Okay. So and Rn is normal reaction. Okay. So equating these, f dash is equal to mg sin theta and ma, and f dash is your mu Rn. Okay. Mu Rn is your Rn is your mu mg cos theta. Okay. So this is your force of friction that is preventing its sliding motion. Okay. So it is balanced by weight of the crater uh, along the along this plane, and acceleration of crater along this plane. Okay. That is F dash is preventing, F dash is the force of friction between truck and crater, so that there is no relative velocity of truck and crater. Okay. And this ma is of truck, sorry, this a acceleration is of truck, so the crater is also moving in this direction with an acceleration of truck, with an acceleration of a. Okay. So there is no extra velocity of crater. Okay. So f dash is your, then f dash will be your ma plus mg psi theta. Okay, and f dash is nothing but this proportion is to normal reaction, and coefficient proportion is mu. So mu, it is mu g and mu mg cos theta. So putting here mu mg cos theta, we can find out a. Okay, we have all the values. M is your 100, mu is 0.3, theta is your 10 degree. Okay, and by putting all these values, we can find out a, that is 1.19 meter per second square. So this is the acceleration of the truck at which the crater will not collide if the coefficient of friction between truck and crater is 0.3. Okay. Next, the maximum fluctuation of kinetic energy in an engine has been calculated to be 2600 joules, assuming that the engine runs at an average speed of 200 rpm. The polar mass moment of inertia in kilogram meter square of a flywheel to keep the speed fluctuation within plus minus 0.5% of the average speed is. Okay. So the total maximum fluctuation of energy is 2600. The maximum fluctuation of energy is given by maximum energy minus minimum energy. So maximum energy is I omega max square by 2 minus I omega min square by 2. Okay. And I is polar moment of inertia. And omega is your mean speed. Suppose omega is your mean speed, that is given as 200 rpm. So this is your 20.94 radian per second. Okay. Now the coefficient and as the speed fluctuation is within point plus minus 0.5%. So maximum speed is 20.94 and multiplied by 1.05, and minimum speed will be 0.995 multiplied by 0.995. Okay, mean speed into 0.995. So we can find out maximum minimum speed, and we have the formula I omega max square by 2 minus I omega min square by 2. Putting the value here, and E we have, that is 2600. It is 2600. Okay. Putting the value E of E, we can find out I is 592.5 kilogram meter. Okay. Next, consider two states of stress as shown in the configuration 1 and 2 in given below. In the figure given below. From the standpoint of distortion energy, Von Mises criteria, which one of the following statement is true? So here in the first configuration, this sigma is acting this direction and this is tau. Okay. In second configuration, this is tau, this is the plane of tau and this is sigma. Okay. So the which one of the following statement? Option one, option A, one yield after two, B, two yield after one, C, both yield simultaneously. Nothing can be said about their relative yield. Okay. So if we look from this side, in first case, then we have figure like this. Okay, sigma, tau, tau, tau. Okay, so we can find out Prince processes. Okay, Prince processes is given by this. Okay, and uh, in this plane, okay, from this we will find out principally along this plane. Okay. And in this plane there is no normal or shear stress. Okay. Or in this direction there is no normal or shear stress. Okay. In this plane, in this plane there is no normal or shear stress. So the principal stress is zero. Okay. So sigma 1 is this, sigma 2 is this, sigma 3 is this. Okay. Now putting in the equation, we will find out shear strain B. We find out the shear strain. So equation is sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square plus sigma 3 minus sigma 1 square divided by 12g. Okay. So putting the value of sigma 1 and then sigma 2. Sigma 1 is your the value of sigma 1. Sigma 1 and sigma 2. This is your sigma 2. Okay, here sigma 3 is 0 and this is your sigma 1. Okay, and this is sigma 1 minus sigma 2. And sigma 1 minus sigma 2 is your nothing but this will be 0. Okay, and this will be square will be sigma square plus 4 tau square. Okay, so this will be the this is the difference between sigma 1 and sigma 2. And this is sigma 2. Here this is sigma 3 square. Okay, so solving this we get strain energy as you can solve by your own. Okay. Sigma square 3 tau square by 3. Okay, so in the second case, this is the plane of third principal phase. Okay, and here only on this plane only tau is acting. Okay, so we can find out the principal stresses on this plane. Third principal stress is your sigma, or we can say first principal stress is your sigma, and other two principal stresses are tau and minus tau when only pure shear is active. Okay. So from this we can find out shear strain energy, putting the value of sigma 1 as sigma and sigma 2 as tau and sigma 3 as minus tau. So solving this we can get the sigma square plus 3 tau square divided by 3. So from this is your U1 and this is your U2. The value is same. So the shear strain energy is both the cases, both the value is same. So both will simultaneously. So answer is your C. Okay. Next, a rigid link PQ of length 2 meter rotates about the pinned end Q with a constant angular acceleration of 12 radian per second square. When the angular velocity of the link is 4 radian per second, the magnitude of the resultant acceleration in meter per second square of the end P. Okay. So this is your Q, this is your P, and its angular velocity is 4 radian per second. Angular acceleration is 12 radian per second. Length is per second square, and the length is 2 meters. Okay. So it will be having two components. One is tangential component of acceleration, another is centripetal component of acceleration. The tangential component will be acting perpendicular to a link 2P and the centripetal component will be acting towards center. Okay, so by finding out the result of these two components, we can find out the total acceleration. So the velocity of point P is your omega into length of link, that is 2, omega is 4. So the velocity is your 8. Okay. So the centimeter component is either you can say even like omega scale into PQ or BP scale by PQ. So this is your centimeter component, that's 32 meter per second square. And the initial component is alpha into PQ. Alpha into PQ. So the initial component 12 to 24. So by scaling, adding both of these components, we can find out resultant acceleration. So answer is here 32 square plus 24 square root 40 meters per second square. Okay, so answer is 40 meters per second square. Next, a spur pinion of pitch diameter 50 mm rotates at 200 radian per second and transmits 3 kilowatt power. The pressure angle of the tooth of the pinion is 20 degrees. Assuming that only one pair of teeth is in contact, the total force in Newton exerted by the tooth of the pinion on the tooth of a netting gear is, okay. So this is your tooth, okay, and this is the common line or a fixed line, okay, and the force is transmitted along this line, and this is the uh, along which the resultant force is acting, okay. So the this line and this specific line makes an angle that is total pressure angle, that is phi, okay, and and total force is acting along this. So Ft, this is part of this Fr is transmitted from one gear to other gear, and Fr is the radial component of this force. Okay, in case of spur gear. Okay, so this is the mm, uh, this is all about forces. Okay, now diameter of pinion is so the one is here, another is smaller is pinion. So pinion is here 50 mm. The speed of the pinion is here 200 radian per second. Okay, 200 radian per second. And power transmitter is given 3 kilowatt. Okay, and pressure angle is 20 degrees. So from the power transmitted, you can find out torque. So that is 2 pi n by 60. N is your n is given. N is your uh, n is n is not given. Omega is given. Okay. So 2 pi n by 60 is given. So this omega is 200 radian per second. Okay. So from this we can find out torque. Okay. And that this torque is being transmitted through this line. Okay. FT fixed line. Okay. Or contact line. Okay. So so this is a force transmitter, and FT is force transmitter is nothing but, sorry, this is a torque transmitter. Torque transmitter is nothing but uh, force into radius, and radius of pinion is we have that diameter of pinion is 50 mm, so radius of pinion is 25 mm. By putting this we can find the FT, and the resultant force is this. Okay, this is the common tangent to pitch circle. Okay, this line is common tangent to pitch circle. Okay, this is a pitch circle. Okay, so the force is transmitted along the common tangent to pitch circle. Okay. So this is the FT. The FT we find out. So from the FT, as it is the component of Fr, so we can find out FT by cos phi is the Fr. So Fr is the resultant force. F capital R is the resultant force. That is 638.5 Newton. Okay. Next, a spherical balloon with a diameter of 10 meters shown in the figure below is used for an advertisement. The balloon is filled with helium bracket RHE, characteristic gas constant of helium is 2.08 kilojoule per kilogram per day Kelvin at ambient conditions. of 15 degrees Celsius and 100 degrees kP. Sorry, 100 kP. Assuming no disturbances due to wind and maximum allowable weight in Newton of balloon and balloon material and rope required to avoid fall of balloon are air is that and actual gas motion for air is 0.289 kilojoules per kilogram per degree Kelvin. Okay, so this is your balloon and this is this balloon. Okay, now in balloon there is a helium gas. Okay, and the helium gas which is filled in balloon is displacing air. Okay, so the whatever air is displaced that exerts buoyant force on the balloon. Okay, so this is the buoyant force exerted by air on the balloon. Okay, and which will act in upward direction. Okay, and now this balloon has been filled by helium. Okay, and helium has some weight, so its weight will act in downward direction, and weight of balloon and rope will also act uh, in downward direction. Okay, so equating these two, uh, we will equating these three, we will find out weight of balloon and rope. Okay, so buoyant force is weight of air displaced by balloon or helium. Okay, so weight buoyant force will be in upward direction. Okay, the weight of air displaced is the volume of air displaced. This is volume of balloon into rho g air. Okay, so when the volume of air displaced is the volume of balloon. So rho g air. Okay, and volume of balloon is and r is radius of balloon. Then the volume of balloon is pi 4 by 3 pi r cube. R is radius of balloon, that is 5 meters. Okay, so volume of balloon is this, and now the pressure, ambient temperature and ambient condition are given. That is 15 degrees Celsius and 100 kP. Okay, from this we can find out density of air. Okay, so that is T is 288 Kelvin and P is 100 into 10 to the power 3 meter and R is 288. So from this we can find out rho. So rho for air is now 1.2061016. Okay, so we can put this value here to find out the buoyant force. Okay, or volume of find out the buoyant force. Okay, or weight of air displaced. Okay, or this is buoyant force. Okay, so buoyant force will be here 6171.2 Newton. Okay, now the weight of the helium is volume of helium inside the balloon into rho of helium and g and rho of helium, the pressure and the temperature inside the balloon are given. Okay, so by using that ideal gas equation, these we have found out V is same for volume of air or balloon. Okay, this is given 523.59 and RH is given, that is 2080. Temperature of the inside the balloon is here 28 degrees Celsius. Okay, and P is also the pressure is same in that. Okay, so from this we can find out rho H. And now after finding out rho H, we can find out weight of helium. This is volume. This is rho. This is mentioned as this is 857.44. That is weight of helium. Okay. Now, the buoyant force is acting in upward direction and other two forces are acting in downward direction. So balancing forces we can have. We have two forces, that is weight of helium and buoyant force. So weight of balloon and rope can be found as force. Weight of balloon and rope is 5313.85 Newton. Okay. Okay. Next, a hemispherical furnace of 1 meter radius has inner emissivity epsilon is equal to 1, has inner surface emissivity epsilon is equal to 1 of the roof maintained at 800 degree Kelvin while its floor emissivity 0.5 is kept at 600 Kelvin. The Stephen Boltzmann constant is 5.668 into 10 to the minus 8 watt per meter square per degree. Uh, watt per meter square Kelvin code. Okay. The net radiative heat transfer from the roof to floor is. So this is our roof. Okay, and this is our floor. Take this floor as 2 and roof as 1. Okay. Its temperature is given as 800 degrees Celsius, emissivity is given as 1, and R radius is 1 meter. Okay, and emissivity of this 2 is here, surface 2 is here, 0.5. Okay, now this network diagram is like that. 1 minus from 1 to 2, we take distances from 1 to 2. The distance of 1 is 1 minus epsilon 1 divided by epsilon 1, and distance of the space is 1 by f12. Okay, and this for this it is 1 minus epsilon 2 by epsilon 2 a1 by okay. So this is the network diagram. Okay, so a1 is area of this surface area of this, and it is area of this. Okay. So now radius of hemisphere is 1 meter. So area A1 is just pi by 4 R1 square by 6, because it is hemisphere. So we take half the area of sphere. Okay, that is 2 pi r square. And now this is the surface exposed. Uh, this is the surface of the floor that is exposed to hemisphere. Okay, and this will be like a circle. Okay, as this is in hemisphere, so this is like a circle. Okay, so its area is pi r square. Okay, so A2 is a pi r square, A1 is here 2 pi r square. Okay, the emissivity of hemisphere is here 1, emissivity of floor is here 0.5. Okay, so these data are given. Now for this, we have all the data F11, F12, A1, A2, but we don't have this F1. To find out F12, we'll use this choice. But some of the shape vector will be, but F11 plus F12 is 1. F11 is 0. F11, F11 is 1 is this one. Similarly, F22 plus F21 is also 1. Okay. F22 plus F21 plus F22 is F22 will be 0 because this surface, this horizontal surface cannot see itself. This sphere can see itself like this. Okay, but this horizontal surface or horizontal circle cannot see itself. So F22 is 0. So it means F22 is 0. So it means F2 is 1 is 1. Okay. Now using reciprocal theorem, we find this F12. So A2 F21 is equal to A1 F12. Okay. Now we have A2, that is pi r square, and we have A2 pi r square. So F12 is here 0.5. Okay. This is here 0.5. Okay. Now we have F12 also. Now we can put this is your resistance, and this is the uh, black body transfer. Okay, and this is resistance. Okay, so this is sigma A1 T1 minus T14 minus T24. Okay, so putting the values, we can sigma is your 5.6 into minus 8, and A1 is your 2 pi R1 here. T1 is 2 pi R here. Okay, and T1 is 800, T2 is your 600. Putting the values, and epsilon 1 is here, uh, epsilon 1 is 1, epsilon 2 is 0.5, okay, f12 is 0.5, and this is a1 is a 2 pi r square and a2 is pi r square. Putting the values, we can get 24937 watt or 24.927 kilo. Next, water flows through a 10 diameter and 20 250 meter long smooth pipe at an average velocity of 0.1 meter per second. The density and viscosity of water are 997 kilogram per meter cube and 855 in 10 power minus 6 Newton second per meter cube respectively. Assuming fully developed flow, the pressure drop in Pascal in pipe is okay. Diameter of the pipe is your 10 mm. Length of pipe is 200 meters. Oh, sorry, 250 meters. Average velocity is 0.1 meter per second. Density of water is 997. Okay, 997 kilogram per meter cube. Viscosity of water is just 855 into 10 minus 6 meter per second. Okay, these data are given. Okay. Now the node number as the flow is uh, to try to know the type of nature of the flow, we will find out the node number. So the node number is rho VD by mu. Putting rho is equal to 997 and d point 1 d 10 by 1000. Okay, mu 850 by 850 by minus 6. Okay, so it comes out as 1166.0. So it means the flow is longer as this. The node number is less than 2000. Okay. So when the flow is laminar, the friction coefficient is given by this 16 by RE, and RE is your 11 6. Okay, so F is your 0.0137. Okay, and the head loss due to friction is always given both laminar and turbulent flow is 4 FLV is divided to E. When F is your for laminar flow is 0.0137. So answer is putting the value of BL is your 250 and B is just 0.1. These things are given okay, and B has 10 mm. And okay, putting these values, we can find out 0.69, the head has 0.69. Okay, and then we can find the question. So, rho GH is rho is your 997. Okay, and G 950, 928. H is this, so it will be 6829.45 meter per meter. Okay, next. A material P of thickness 1 mm is sandwiched between a metal P of thickness 1 mm is sandwiched between two steel slabs as shown in figure below. A heat flux of 10 watts per meter square is supplied to one of the steel slabs as shown. The boundary temperature of the slabs are indicated in the figure. Assume thermal conductivity of the steel is 10 watt per meter per Kelvin. Consider one-dimensional steady state conduction or configuration. The thermal conductivity of the metal P is okay. This is the slab given. Its temperature. This is this temperature is 360. Okay, this dimension is 21, 21. Okay, and the thickness is given as 1 mm. The thickness is given as 1 mm. And heat supplied per unit area is 10 kilowatts per meter square. Okay. And thermal conductivity is also to thermal conductivity slab is 10 watts per meter per unit area. Okay. So this is so drawing its resistance diagram. So all these are in series. So first, second, and third, two slabs and one sandwich which is series. So resistance are in series. Okay. So resistance for this is x1 divided by K A1 A1. Okay. And for this is x2 by A2 and for this is f3 K3 A3. Okay. And this conductivity is K and this conductivity is 10. This is 10. Taking unit area. Okay. A1 is equal to A2 is equal to A3. A1 is this area. Okay. So taking the area same for both for all. So R1 will be x1 by k1, R2 will be x2 by k2, and R3 will be x3 by k3. Okay. So x1 is your 20 mm and x2 is your 1 mm and x3 is your uh, again 20 mm. Okay. So putting the values, we can have A is A is taking A as unity. Okay, so we can have this value of R1 and R3 as 20 is mm and 20 in mm, so 20 by 1000 millimeters by 10. Okay, taking A as unity. Okay. Similarly, this will be R1 and this will be R3. With R2 is the 1 mm thickness, so 1 by 1000. Okay. So the heat transfer per unit area is now that the factor which is favoring the heat transfer, that is intelligent, and that divided by the factor which are resisting the heat transfer. Okay, so that will be equal to Q. So putting the values, we can find out putting the value. K is the conductivity of this sandwich. So putting the value, we can find K. Okay, so K is your 0.1, and solving it, K is your 0.1 watt per meter degree or watt per meter per degree. Okay. Thank you. We'll solve rest of the paper in next week.